So thanks for the invitation also from my side. I'm going to give a quick overview of activities that we've been doing in terms of combining data and modeling in Rift. And I'm going to move from US to Europe and focusing on works that we have been doing on the Upper Rhine Graben. A bit of a introduction in terms of the geodynamic history of the Graben. The Graben itself belongs to the larger European Cenozoic rift system. If you look at the Graben structure, it's a pretty thin, let's say, Graben. It's 30 up to 40 kilometer wide and 300 kilometer long. So a kind of a question to the community and the geodynamic community that listening to this talk is how you can actually form such a thin Graben in the end. It sits on a heterogeneous crust. You see here in the map the different domains that have been amalgamated and collide during the Variscan orogeny. The pre-reef sedimentary sequence dates back to Carbonifero Mesozoic and are associated to rifting in the lower Permian, which is also accompanied by volcanism, while the syn and post-reef sediments are Cenozoic in age and are correlating to a east-west extension that happened in the foreland on the Alpine belt with the possibility of localized mantle uplift. So the interest from our perspective is that the Rhine Graben is also a target for mid and high enthalpy in terms of deep geothermal energy. We have all the features of interest. We have high geothermal gradient, not as high as in Los Alamos. So we are around 100 degree per kilometer. We have major fault zones. We have active fluid circulation in terms of mineral and thermal waters and so forth. There are 9 different geological reservoirs in the different formation, and those reservoirs sum up to 186 tetrawatt hour per year of technical potential. In principle, it's around 5% of the annual energy demand in Germany. This is actually the size of the resources that we could, in principle, extract from this area. Activities are ongoing in the sense that we have 6 active deep geothermal power plants that are operating, and 4 is being cancelled because of induced seismicity. And I'm gonna discuss a bit of how we can also make use of those modeling activities in terms of reducing the induced seismicity and the shut-up of those power plants. The good part of that we have in here is that we have an extensive database. You see in the figure in the left, we have more than 400 exploration well, more than 500 production well. We have 2D reflection seismic profile, different 3D geological models from the different geological surveys that we combine during a PhD by Jessica Freimark to construct a 3D lithospheric scale structural model that is consistent with all the data, but also with gravity. And this is actually the model that we've been using in our studies. In order to consider a bit of an introduction also about the modeling activity. So the second component, apart from the geology, is to have a software or a computer code that can deal with can simulate all the physics, and this is something that we're also developing in our group. We have developed an open source software that take all thermo, hydromechanical, and chemical processes in fracture porous media. The idea is classical in terms of the closed form solution of the equation. So we are solving for fluid and solid mass balance, both for the porous media and the faults. We couple that to an internal energy balance for the porous media and the faults, and then we consider faults mechanical as lower dimensional distinct elements in terms almost like a zero thickness cohesive elements that have frictional behavior. And we have been also coupling the code to Frixie library in order to also implement reactive chemistry. The approach that we are following in order to understand the geothermal potential and also the exploitation of those resources is a multi-stage approach. We start at the beginning taking a perspective of the large scale. So we run what I call here a thermorheological model of the entire Graben. So we are considering the full lithospheric scale model, and we try to understand what is the fingerprint of the different configuration, crust, mantle, and sediments on the thermomechanical state. What we actually observe here in moving from the left to the right is that we see a systematic variation in space of the distribution in earthquakes and in their frequency magnitude. So you see here a profile of the B value extracting around the rift, while the figure here showcases the different earthquakes color-coded by their magnitude. And we link this spatial distribution to the inherited structure, mainly in the crust. As a matter of fact, what we observe is a correlation between the rheological configuration that we represent in the figure on the right in terms of the mechanical thickness to the earthquake distribution, not only laterally but also in depth. This is the figure in the middle where we show the seismogenic depths, and these are only considering tectonic earthquakes. We also observed that the degree of mechanical decoupling in the crust correlates in an inverse manner with the local temperature condition, and that results in a kind of subdivision in terms of the rheological configuration of the Graben that presents a weak crust in the southern sector, where we also have a clustering of low magnitude earthquakes and this increase in B values, while we have a northward increase in the depth of hypocenters that are related to a thickening that you may observe in here of the brittle crust and the deepening of the brittle ductile transition. And this also occurs when we move off the Graben. In terms of observation and how good our model are to feed data, what we actually try also to validate and calibrate the model in terms of observation. We have more than 350 wells that sum up to 2.6 thousand temperature measurement. You'll see an histogram of the difference between the outcome from the model and the measurements at different depths. There's a pretty decent agreement between model results and observation. We have around 78-80% of the observation that stays within a plus minus 10 degree. And what we notice if you move to the right figure on the slide is that the highest difference are especially confined to a depth interval between 1 to 2 kilometers within the Graben itself. In a second stage, we also perform a global sensitivity analysis via physics-based surrogate models in an attempt to optimize the model calibration. And this is actually the figure in the middle. And what you see here basically is that the main outcome of this global sensitivity analysis is that indicates that apart from the deeper configuration, so the role that comes from the crust and the mantle, we have also an importance in terms of sensitivity of the model outcome that comes from the Cenozoic rift sediments. And that highlights the potential role of the active fluid circulation in terms of both advection and convection in those porous sediments within the Graben in order to explain the present day thermal configuration. So that brings us to a second model, so a second stage of our study, where we focus only on the sedimentary component and try to run a hydrothermal model of the entire Graben. This is actually summarized in the figure on the left, where you see the groundwater component within the Cenozoic sediments in terms of flow path, which are color-coded by the vertical component of the fluid velocity, where orange indicates uplift and blue indicates downward flow. And in principle, we obtain a consistent image of the main characteristic of the hydrothermal setup in the Graben, we have a topography-driven basin-wide fluid flow that goes perpendicular to the main rift axis. So we actually enter from the Graben shoulder to the rift center. And then we have this north-northeast directed flow parallel to the main axis of the Graben in the rift in the center, which more or less follow also the outline of the River Rhine, which is actually sketched by the blue curve in the figure. We also notice that we have a pronounced upflow of hot fluid that depends on buoyant flow anomalies along the central reef axis that is consistent also with the observed localization of the surface heat flow and the higher temperature that we observe in the area. And all the surface thermal manifestation that we have in terms of mineral and thermal water spring are also more or less spatially coincide with the predicted upflow areas that we have in the model. We have a less match in the south, and we related that to the presence of small-scale structure in terms of minor faults that are not included in our model that also promote the mechanical weakness that we observe in this part of the Graben.
Sorry, Mauro, you are
Yes.
at 11 minutes. You are now at
Yeah,
11 minutes.
I'm almost done.
Go
So the last stage of our activity is to go and zoom in a bit better into actual reservoir modeling. And I'm presenting today just a simple example of how this modeling activity can also help in the operating stage of those geothermal reservoir. This is a work done within an European project, DTGO, together with colleagues in Strasbourg, where we're trying to build what we call here a digital twin of a project that is called Geoven, where it consists of two wells that have been drilled in 5 kilometers. Here you see the sketch of the well. We are close to Strasbourg, and resulted in trigger seismicity due to the stimulation of the two wells. And I mean, the open question that we wanted to address is the presence of a seismic shadow between the two clusters. So we have a first cluster of event that is actually close to the well, and then we have a second cluster of events that have been triggered by the operation that space 5 kilometers apart. Apart from that, we also have, we need to explain the 10 days time delay between the northern cluster and the southern cluster, and also additional component. In order to create the digital twin, we set up a thermohydromechanical model that we calibrate with respect to in situ stress condition. All the parameters are derived from an existing geological model and also from inversion analysis, analog outcrops, and production test data. This is an example of how the events and the earthquake magnitude looks like. What we have a relocated cargo from the people in Strasbourg, and what you observe here is also a variation in B value that is more or less spatially, but not temporally. So we also correlate them to inherited structure. And when we try to model the stimulation, what we actually see is that both in the northern cluster and in the southern cluster, the spatial footprint of the seismicity can be easily captured by a simple pore pressure diffusion. The problematic part of such a simple model is that the possibility to explain the fact that we don't have or we don't observe any seismicity in between these two clusters. And this is actually something that we try to explain by looking at the hydrothermal imprint of the area. So what we did basically is to run experiments in order to reproduce the natural hydrothermal state of the reservoir, both in terms of measured temperature profile and in terms of observed heat flow. And what we found out is that only by considering active convection in the upper granite domain, which is the target reservoir of our its target reservoir, we can actually estimate, we can provide the best estimate to both metrics. And actually, this is an image of how the convective setup in the reservoir looks like. And what we found out is that considering this additional component of this deep hydrothermal circulation within this upper granite, we can actually have localized weakening due to this localized hydrothermal system that is also promoting weakening of the fault and may explain the reason why we do observe a cluster of seismicity 5 kilometers apart from the actual injection and the lack of seismicity in between because there I mean, the fault has not been weakened before. So to conclude, we actually can provide evidence that the sequence of induced seismic event and Vendemai project can be considered as an example for a typical trigger sequence of induced events that are related both to the tectonics but also to the local hydrothermal setup. And I think the lesson learned that is interested in here is that uh, our activity showcase the relevance to incorporate also detailed geological information in seismic hazard assessment in a sense that we need to go a bit beyond only to focus on injection practices like traffic light system, but giving sometimes a greater weight to the influence of the pre-existing hydrogeological condition that can explain a lot more than only looking at the engineering parameter. And I stop. Sorry for not being in time.
No, it's okay. There's still time, a few minutes for questions. Thank you,
Yeah.
Mauro. There are questions already on the chat. The first one from Yao Li says the model appears to assume all fluid are meteoric in origin. Is there a possibility of a deep sourced hydrothermal fluid? And in addition, from Cindy, the question is, and magma degassing, are the fault zones porous?
Yes, so I can start with the first question. When we talk about fluids within the Cenozoic rift sediments, we do have evidence from fluid chemistry that is mainly of meteoric origin. So we do not have any evidence for deep source hydrothermal fluids in the area. So at least in this sense. And in terms of the faults being porous, faults are depending on the local, let's say, condition can be barrier or porous. And this is something that we careful analyze via data from the different with different group of people. So we know in principle, I think what is actually interesting is that it seems to be that the boundary faults that actually form the graben are porous. So there's a lot of evidence that might be permeable, those faults are permeable and might promote local scale convection because most of the thermal springs are also observed actually aligned to these boundary faults. Other faults are also, and also some other surface manifestation can be explained by local fault activity.
Okay, there's also another question about how well can permeabilities be constrained and how sensitive are the results?
Well, the permeability or the constraints on all the material property depends on the scale. When we go to the reservoir scale, so to the engineer reservoir scale, we have really well constrained values because those are coming from field tests, those are coming from seismic inversion, those are coming from outcrop. So we are pretty, let's say, confident of our values. On a regional scale, those values are best estimates. And as a matter of fact, we're also trying to assist our best estimate via this surrogate and ensemble modeling approach, where we can also highlight the degree of uncertainties in the material properties, just to be more, let's say, to give a sort of a weight in the values that we're actually being used, but it's true. So on a regional scale, those values are not that certain.